Okay. So, nuts, bolts, and fasteners. Nuts, bolts, fasteners. This is going to lead into taps and dies. Taps and dies, in order to use those, we got to understand drills. So these are all materials, and these are all processes. Does anybody know what this is right here? This kit. I got a couple of different things. If you've already seen it, don't mention it. How about you? You know what these are? Everybody seen these? These are taps, and these are dies. Right? These separate the men from the boys. Okay, in terms of mechanics, in terms of fabricators. If you don't have a set of taps and dies, you can't repair broken threads. Okay, you can't chase them. You can't create your own from scratch. A tap will create an internal thread in a hole. That's what you guys are going to be doing. And a die will create an external thread. It'll go around a bolt and fix a thread, or you can create threads from scratch. So everybody's going to use both of those. That's what we're finally going to do. So next week we'll be out in the lab working with taps and dies. But first, we need to be able to identify different types of fasteners. And if I walk up to a bolt, I am going to see 6 sides. Let's go with 2 different bolts here. I'll try to squeeze it in here. Be a little crooked. Now, 2 different bolts. I walk up to the head. If it is blank and it has nothing on it, chances are it is a standard bolt. So you're going to see bolts that are blank or have dashes, or some are going to have a number. Now, this will be a standard bolt / American system, and the number will be metric. All right, the rest of the world. Most of the nuts and bolts that you use to assemble a deck or basic fabrication when we go out are going to be standard bolts. If you're taking apart something that's already been built, chances are it's got metric bolts, especially cars and engines nowadays. So if I pull any bolt out of here, I see a head. It's got 3 dashes. 3 dashes mean that this is a standard American bolt. Well, another bolt. This little guy says 8.8. Do I grab a metric wrench or a fractional wrench? Metric, you got it. So, let's take a look at the different grade marks. And those 3 grade marks represent something that we have to understand. So, we go back here. And we get up here. We can see that the different grade marks for bolts that you'll see in the hardware store or in life. Rarely do you ever see anything below 8.8, 9.8, and then 12.6 is the strongest bolt. 3 dashes means it's a grade 5. The higher the number, the stronger the bolt. Grade 8 is the strongest. So here's the rule of thumb. 3 dashes, add 2 to get the grade. 6 dashes is as strong as you're ever going to see. That's a grade 8 bolt. Okay? It's going to cost a little more. It's going to hold more. Okay? It could take more stress. You can get it tighter. So, grade 5, normal. Grade 8, strong. Most of the bolts we have in our bolt caddy are grade 5. Now, how does a nut, bolt, or fastener work? Let's take a look at a video here. Nice little cartoon that can describe the physics of it.
Eureka! The story so far. If you could
divide the force you get out of a machine by the force you put into it, you will discover the mechanical advantage of that machine. But since every machine involves contact between moving surfaces, its mechanical advantage will always be reduced to some extent by the force of friction. There's a lot of friction involved with the inclined plane, but hardly any with the lever. And now, the screw and the wheel. How many different types of simple machine do you think there are? 2. There are only 2 basic machines, the inclined plane and the lever. These are the mother and father of every machine in the world. All the others are merely variations on the same theme. For example, there's a beautiful machine. No, not your car. The road. Yes, the road. A winding mountain road is a machine too. Well, suppose the road didn't wind. Suppose it went straight up the side of the mountain. This is a much shorter way to the top, isn't it? And yet it won't do you much good, because the engine of even your magnificent automobile hasn't enough force to lift your car straight up. But suppose we make the road long enough and the slope gentle enough for you to drive up the mountain with ease. What have we done now? Yes, we've made the road into an inclined plane, a simple machine. But that's an expensive way to go up a mountain. It requires an awfully long ramp. What if we wrap the inclined plane round the mountain instead? Now we're back where we started, with a winding mountain road, which is really an inclined plane in disguise. A twisted inclined plane, if you like. There are twisted inclined planes all over the place. This includes every device that has a spiraling, corkscrewing action, and which allows you to trade extra turning distance for reduced force, either to help you lift things or fasten things together. Here is the commonest example of all, the screw, which is, in fact, the very name which physicists give to every type of twisted inclined plane, the screw. So that's one of the descendants of the inclined plane. Hang on a minute. Can you give me an example of a simple machine that is descended from the lever? Well, you're holding one in your hand right now. Yet another machine that doesn't look like a machine. I know. But have you ever tried to open a door without a doorknob? You haven't got enough leverage, have you? That's where the doorknob comes in. It's a direct descendant of the lever, like this, or this, or this. They're all children of the lever. How come? Well, a long time ago, some very wise men were looking at a lever one day, when they suddenly thought how nice it would be if the extra force the lever gives you to lift something from here to here, say 4 times the force, because one lever arm is 4 times the length of the other. They wondered if this extra force could be extended through 360 degrees. In other words, they wondered if they could make a circular lever, a lever that would go all the way round. And while they were at it, they made up a new name, an axle. With a center where the point of the fulcrum used to be, and the short arm of the lever now running from this center to the outside of the axle, and the long arm running from the center of the axle in the opposite direction. Now when you push the lever with a force, say, of 100 Newton, you can turn the whole axle around with a force of 400 Newtons. And that's how you're able to open doors and steer cars and ships and pull up anchors with such ease, thanks to the ancient wise men and their circular lever. Yes, congratulations. You've just reinvented the wheel.
Okay, so if we're looking at bolts here, I'm going to kick a couple lights on here. We are looking at these bolts. The common rookie error is most people will think that 1/2 inch means get a 1/2 inch wrench, get a 7/16 wrench, 3/8, 5/16 quarter. That's not what that means, okay? So if you say that I got a 7/16 bolt, all right? 7/16 is the diameter right here that you'd measure with a micrometer. The diameter of the threaded area. So this is 7/16, 3/8, 5/16, a quarter. What do those dimensions look like? Fractions, right? Fractions like we read on the ruler. Anything less than quarter is going to be a number. So the next one below a quarter is a number 12 screw, then a 10, then an 8, then a 6, then a 4, then a 2, then a 0, then a double 0, triple 0, quadruple 0. Everybody's seen really small screws in their phone, eyeglasses. Those are the teeny ones, the double zeros. You need small bits. We're going to focus mostly on these threads. Rarely are we creating the threads smaller, okay, on our projects. So what you need to know is a 3/8 bolt will probably have a 9/16 wrench. A 1/4 inch bolt, 90% of the time, you grab a 7/16 wrench. The two most common wrenches you're going to use in your life probably are going to be the 7/16 and the 10mm wrench. A lot of components are held together with 7/16 wrench and a 10mm. Now here's why. 7/16 will fit perfectly on a 1/4 bolt, which is probably the most common bolt used to fasten general things together. And a 10mm fastens a 6 by 1.0mm bolt. Well, what the heck's that mean? Okay. So that's our next step. Want everybody to get out some notes. If I'm drawing, you're drawing. So let's draw a bolt, a side view of a bolt, and try to understand it. So I'm going to draw a head of a bolt. I'm looking at the side of the bolt and just make a bunch of V's. Go down and make a bunch of V's. If you don't have the exact amount, it doesn't matter. In between, I'm going to make some lines. Those are kind of giving you the perspective that this is a bolt. This is the head right here. Obviously, those are the threads. Now, we're going to talk about standard bolts first. And then we're going to talk about metric. So, a standard bolt can come in two things. NC and NF. N stands for national. Course. This one stands for national. Fine. And our bolts, if we look up here on our chart here, can only come in certain sizes. UNC, UNF. A 1/4 inch bolt is either 1/4 20 or 1/4 28. Well, what does that mean? All right. If we look here, let's say 1/4 20. 20 is TPI. Threads per inch. So if I take a ruler up to any standard bolt, I should be able to measure from one point, and if I have an inch of threads, the 1 inch mark will land perfectly on some other thread. So if this is 0, this is 1 inch. Let's see what this is. 1, 2, 3, 4, 5, 6, 7, 8. This would be 8 TPI. Now there's nothing that says 8 up there, is there? No, that would be, there's only one bolt. There's actually a couple bolts that have 8 threads per inch, but it's not on the list. It would be a 1 inch bolt. So a 1 inch bolt has, in course, has 8 TPI, 8 threads per inch. Now, let's say that we measured across, and this thing was 20 threads per inch, so 20 TPI. Right here, the distance here across this would be 1/4 of an inch or 0.250. 1/4 of an inch or 0.250. 1 divided by 4 gets you 0.250. So we got to start using decimals and fractions. We're going to have a chart that converts. So let's say that's a 1/4 inch, 20 TPI. Now we need the length. That's from the end of the thread to where the bolt head starts. All right, so that's only the threaded portion. This head, you're going to notice, can come in different configurations. Okay, the head can be round, square, or hex. There's 12 points. There's all different types of head designs. What we really care about, though, is the thread and identifying. Now let's think back to that cartoon. Little guy's driving his car up the hill, right? One of the paths he takes, they draw it real quick, so he gets to the top of the mountain real fast. That would be a coarse thread. Taking more turns to get to the mountain is a fine thread. Now, which one could you put more torque on? Which one do you think? Coarse or fine? Coarse, how come? It's a bigger thread. Most people think that right away. It's bigger thread, bigger contact. So a unified fine, national fine, is going to have more turns, but it's easier to drive up the hill, right? Just takes longer. So this one we can put more torque on, right? Most common though, you're going to see our coarse thread. So if I take a look here, here's 2 3/8 bolts. One's coarse, one's fine. Same diameter. One's got more threads per inch, right? One is going to take more turns to turn it in. Yes, but it could take a little more torque, okay? Usually the fine bolt is a little higher grade, but now let's go to metric. So I'm going to erase this and draw a fresh one. So we'll draw a new one here. So we're going to draw the bolt head. Let's draw a bunch of V's. Okay, now we still have to care about the diameter. The diameter here is going to be in millimeters, so this is metric. Now, all threads, UNC, UNF, and metric, if we look at the shape of the thread, each one is going to be 60 degrees. Okay, in between. Cuts are going to be 60 degrees across the world. There was one weird one, probably went till the end of the 60s, called Whitworth, and that was 55 degrees. That's no longer in use. What that's pretty interesting though is that metric and standard, they just use the same angle. Okay. Now, metric will be in millimeters. Let's say it's in whole millimeters. 4, 5, 6, 7, those are rare, 8. Then it skips to 10, 12, 14, 16 millimeters in diameter. Remember, we've got 60 degrees here. But here's what's different on metric. On metric, we can have fine and coarse bolts, but they do it a little differently. They measure the distance between the thread, and that's called the pitch, and that's measured in millimeters. So let's say that this bolt right here is 10 millimeters, and this is really hard to measure with a ruler. But a 10 millimeter bolt can come in 1.0 pitch, 1.25, 1.50, and a real coarse one would be 1.75. So you could have 4 different 10 millimeter bolts. Some of them are going to be more rare than the others. Harder to find the 1.0s, common 1.25 and 1.5. So this one, let's call it a 1.5 millimeters. So this is 1.5 millimeters. The threads are apart. Now the length, again, is from the head start of the head to the end of the thread. Let's say that that is 30 millimeters. Bolts are going to come in 5 millimeter increments. So you could have a 20, a 25, a 30, a 40. Hundreds of different options. All right? We got to have all the options we could possibly find. So this bolt would be written as 10 millimeter, 10M, 1.5 by 30. So 10 millimeter diameter, 1.5 pitch, 30 millimeters long. Now, how the heck do we find out the distance between them? We're going to use what's called a thread pitch gauge. So we'll take a look here quick and see a thread pitch gauge. Then I'm going to show you a bolt from McMaster Carr off the website, that's the exact bolt that we have on the system. So, go through. So there is the distance between the threads, you can see. Now, these are thread pitch gauges. You use them for metric and standard. Standard's pretty easy to decipher. It's coarse or fine. Now, if this said 1.5, these little shark bite teeth will fit perfectly in a line from that bolt that is 1.5 threads per inch. So, there's a good option right there. That's a thread pitch gauge. Now, if I go to McMaster Carr here, and I go back, I was looking at all these different metric bolts. So I went with, hey, let's go with the strongest bolt, 12.9. Now, look at the pitches. 10 by 1.5. Well, here's a 30 millimeter long. So I click on it, I go to the product detail, and there's a drawing of this bolt. Now, kind of like the one we drew on the board, but much better. So, you can even see the thickness of the head. The length is 30 millimeter, 10 millimeter wide, 1.5 pitch. What size wrench would you put on this, or socket? Can you tell by the drawing? What's that say?
17.
17. You're going to grab a 17 millimeter wrench for this bolt. That's what you're going to do. So let's take a look at this video here. He's going to identify some different types of screws and fasteners we're going to encounter. Nice little job, kind of funny.
Hi, my name is Chris Rogers. I'm an industrial designer and robot builder. This video shows you different types of bolts and just gives you a general overview of some of the variety that's out there, how to distinguish between them, and how you might use one or the other. Bolts come in a variety of different sizes, from the very, very tiny to the very, very, very large. This shows the difference between a screw on the right and the bolt on the left. The screw usually has a point. This is a Phillips head wood screw, and this bolt is a 5/16 24 grade 8 hex head bolt. The difference is this is secured with a nut, and this is threaded into threads in your work. Really. Here's an example of a bolt and a nut being used to secure a couple plates together. You can see on one side it's a hex head, and on the other side there's the threads and the nut securing it. These are some of the different types of bolts, and the first thing you might notice is some of them have thread on only a small portion, and some have thread throughout the whole length. These are called fully threaded, and these are partially threaded. No way. There are lots of different styles. This is a very coarse thread, and this is a very fine thread. So you need to know how to specify that. You're talking about pitch. This shows you the difference in the pitch, or the threads per inch. This is a National Fine, National Coarse, or NC. This is a 5/16 18. This is a 5/16 24, meaning there are 24 threads per inch. Here there are 18 threads per inch. So to order this bolt, I would get a hex head grade 8, 5/16 18 by 1. So hex head, grade 8 is the coating and the hardness. 5/16 is the hole diameter, or the diameter of the shaft. And the 18 refers to 18 threads per inch. And the 1 refers to the 1 inch length. This is a 5/16 24 by 1 1/4. Are you kidding me? Here's an example of where to use this type of bolt. This is a 1/2 inch 20 by 1 inch long, and this is a grade 8. I'm using it to secure this wheel to this aluminum adapter plate. The plate is threaded, and to use it I would simply screw this in by hand and then tighten it using a socket wrench. Get out of here. These are stove bolts, and they come in a variety of different lengths and styles. This one is galvanized for corrosion prevention. This one is used to secure the toilet bowl to the floor. Seriously? They have a round head, and if you notice, this feature right here is a kind of squared off section. These are often found in hinges on a barn, and you fasten this through a hole and secure it with a nut from this side only. This is an application where I've used a stove bolt for security. This is a hasp on a shed. On the inside you can see the bolt goes all the way through and was secured with a washer and a nut. These are lag bolts, and they're typically used in the construction industry to fasten together 2x4s and large timbers. This one's galvanized to prevent corrosion. You might use this to secure a railing to a deck. Here you can see lag bolts being used to secure this 2x4 to this 4x4 on this heavy-duty workbench. They're used simply by pre-drilling the hole and then screwing these in with a socket set or this driver. Ooh. These are what is known as cap screws, and they come in a variety of different sizes and styles. The silver ones are stainless steel, and these are black oxide. These are typically installed with a hex drive or an Allen head wrench, and you can see each of them has their own specific size, so it's important to match the proper Allen head wrench with that head. Really? You'll notice there's a variety of different pitches or threads per inch. This one on the left is a 1/4 which means the hole diameter is 1/4 inch, and the threads, if you count 1 inch, you'll come up with the number 20. So that's a 20 thread per inch, 1/4. Wow. What's great about these is they can be really torqued down, and you can specify the amount of torque you need. You'll find these in machines, tools, and a lot of high-tech gear. Here's an example of where to use a cap screw. This is a 1/4 28 cap screw, and it's used to secure this gear housing to the back half of gear housing on a motor. They use a fine thread because this has a lot of vibration. So to use it, you would simply cap out the back half and then secure.
All right, I'm going to pause that. Notice that he's using a hex head / Allen, and he's putting it in what's called a cap screw. If we look here, why wouldn't you put a hex head bolt here? Why would you not put a hex head bolt in there? Yeah.
Because you can't fit either an open end wrench in it or a ratchet.
Yeah. How could you get an open end wrench in here and tighten it? Or a socket around that, unless that cavity was bigger. But it's small, so small that now we need a cap screw. So we're going to need a hex head, again, standard or metric size. So what do we do with all this? We have to figure out what we're going to do to create an external and an internal thread. So the first thing we want to do is try to master our Amtek Decimal Chart, which to me is the most cumulative chart on the internet in one small package, the Amtek Decimal Chart. I'm going to hand these out. Get one onto the screen here. We're going to try to identify a few things. We can convert decimals to millimeters. We can convert fractions to decimals, decimals to fractions. We can see all the different drill bits, letters, numbers, all on one piece right here, the Amtek Decimal Chart. So let's get that up on to the screen here. And we're going to try to break it down, just do a couple, and then we're going to go into more depth later. Everybody will have a required worksheet for this. Oops. We want that. So here is our Amtek Decimal. I'm going to open it. Alright, same sheet you're looking at, nice and color coded. Yours are laminated. Up at the top, we look, it says sizes, decimal inches, tap size. And it goes sizes, decimal inches, tap sizes. The blue and the white go together. The gray, we'll learn later what that means. That's your tap size, and we're going to figure out how to drill it. So if I just look quick here at 632. I've got my cursor on at 632, back and forth there. I would drill a hole to a number 36, but we'll get to that later. So let's first try to get something easy here. I'll put it up. And it's going to be right kind of obvious. So I'll say, hey, what's 3/8 as a decimal? Okay. 3/8 as a decimal is what? Well, we can do the math. 3 divided by 8. Put a decimal, zeros. 3 goes into 30. How many times? 3. 24. 6. Goes in there 7. 56. And keep going till we're even. 0.375. Is that necessary? No. You could get a calculator quick, but the chart will have everything. If we look here, it's got fractions. 3/8 equals 0.375. Now, something is pretty close, if we look here, in size, and it's not many thousandths more, to go up to a 10 millimeter bolt. A 10 millimeter bolt is 393. This is 375. So it's not that much difference, okay? 10 mil and 3/8. This thing's got conversions for everything. Notice, we're going to see on the white column, ones, fractions, millimeters, letters, okay? Fractions again. All of a sudden we get to Z and it ends. And we got fractions, millimeters. Millimeters, 9.8, 9.75, 9.7. All of that lines up. You're going to have to master this chart, and we're going to use it for our first assignment. The reason being is you're going to get a random bolt. You're going to have to mic the diameter. You're going to have to go to the chart, figure out what fraction of an inch it is. So if I mic the bolt and it's slightly under 0.375 and it had 3 dashes on it, it's a standard bolt, probably 3/8. Then I figure out if it's coarse or fine. Then I use this chart to figure out, hey, what drill bit am I going to use? I drill it, and then I go my tap and die set. I get my tap out, I tap a hole, and a better thread in. So that's what we're going to kick off and master this chart when we come back on Monday. Okay? So let's take a look at it for a little bit. The worksheet for it, we'll start on that on Monday.